Okay, let's begin. I'd like to thank you for attending this Coreform webinar today. My name is Mike Scott. I'm the CEO of Coreform, and joining me is Greg Vernon, one of our chief engineers here at Coreform. I'll be providing an overview of our approach to simulation, just to give everybody a little bit of a kind of an underpinning for what we're trying to accomplish here at Coreform. Then I'll hand it off to Greg, who will do a demo of our new product, Coreform Flex. And then we will move to a question and answer session where we'll go through the questions. Okay, so let me dive in and tell you a little bit about what we're trying to do here at Coreform. We've been around for about 10 years and trying to solve a very difficult problem in computer-aided engineering or simulation. And the problem that really motivated us at the beginning of our time working at Coreform was this problem right here, where if you look at kind of how you spend your time in simulation, you notice immediately that a vast majority of the time is actually what I would call non-value added activity, which means that you're doing things that are preparatory to simulation, but are still peripheral to the thing you're really after, which is to run the simulation and get insight into your engineering design. And this is composed of things like meshing, geometry simplification or decomposition so that meshing can be successful. And then, of course, all of the operations to set up the model. And for many of our customers, especially those who are working in advanced engineering organizations where they have very sophisticated designs, it's not uncommon for them to spend more than 90% of their time doing things that are kind of preparatory to simulation. And so the vast majority of their engineering simulation budgets are going into these activities. And of course, this is kind of just an example of going through the process once for one simulation. If you want to iterate or change the design, oftentimes you have to repeat the process, which makes it very prohibitive to use advanced simulation for design exploration, for example, or moving simulation earlier in the design process. So we set out to solve this problem in a compelling way. What we want to do is develop extensions or advancements to the finite element method that allow us to eliminate these issues without sacrificing robustness and accuracy or range of applicability. So we want to build a simulation technology that is capable of handling linear type phenomena, linear elasticity, for example, all the way up through very sophisticated nonlinear time-dependent phenomena. And the benefits that we're seeing emerge for our customers, and that is exciting to us at Coreform, is that indeed they are able to produce simulation results in far less time. So in particular, we have some customers that may take months building models that can now build these same models in a day or two or a week, depending on how large the assembly is, for example. But the reduction in man hours is quite astounding and helps them really kind of enjoy the process of simulation a little more, because they get rid of a lot of these things that their engineers just didn't enjoy doing very much. And then, as that becomes a reality for them, and the process of building and running simulations becomes simpler, immediately they begin to look at and to think about new ways to optimize their designs through automation. And immediately, many of our customers are already thinking of novel ways to use the technology so that they can actually get to the kind of work that they've always wanted to be able to do. And certainly this automation where you can build models immediately in a robust kind of user intervention free approach has kind of unlocked the ability to explore the design space and optimize designs. So I only want to spend about 10 minutes talking, and then I want to hand it over to Greg so you can actually see the software in action. But I wanted to give you an example that kind of helps pin some of the basic concepts so that you can see how we achieve what we achieve and how things might be a little different than what you would find in traditional FEA. In this example, we've taken this cast part, which is very complex geometrically, and then the challenge is, can we mesh that automatically and run a simulation on it without any user intervention? And the way that we accomplish this is through a technology called isogeometric analysis. And isogeometric analysis really means that you're using the CAD geometry directly in simulation, but even more fundamentally, it means you're using spline functions as the core basis function technology in the finite element method. And the power of spline functions is pretty important because it allows you to then relax some of the constraints on meshing that make meshing so difficult and error prone. So for example, in this case, we take this CAD part here and we immerse it in this mesh that's composed of B splines, degree 2, C1, first order continuous functions. So the derivative is the first derivative is continuous, and it's degree 2. And this is what we call a quadratic B spline. And we immerse this CAD object into this B spline mesh. And then we perform what's called flex meshing, which will essentially trim out the CAD object out of that spline mesh to create our simulation model here on the right. And this trimming procedure is actually fully automated. So regardless of the complexity of the CAD, we can now produce a simulation model automatically. And that simulation model is defined in terms of higher order smooth spline functions, which actually produces far superior numerical methods. So you've relaxed the constraints on meshing while producing methods that are superior to traditional FEA in terms of their accuracy per degree of freedom, as well as their kind of robustness to large deformations, mesh distortion, all of those kinds of things that normally cause trouble in convergence for example, nonlinear problems. And then we can, of course, run a simulation directly on that simulation model. And so this is the basic idea. And this flex meshing step here, I would say, is one of the core innovations at Coreform that unlocks this ability to eliminate a lot of those non-value added activities from model setup. To speak about flex meshing just a little more, we use the term flex because it's flexible, meaning that there's kind of a continuum or spectrum of meshing opportunities or meshing capabilities. On the left, you have kind of the traditional defeature and then produce a body fit mesh. So this would be on the left what you would do in standard finite elements, where the mesh conforms or fits to the CAD body, the CAD volume. And in order to accomplish this, oftentimes you have to remove things like fillets, which is what has been done here, where the fillets have been removed to simplify the process of producing this hex mesh, for example. Then on the right end, the right side of the spectrum, we have kind of the most, I would say, automated approach where you stick the CAD body inside of a grid of splines, a B-spline grid, and perform that trimming operation directly. And then, of course, you can do anything in between. You can produce, for example, body fit in some locations. Maybe you have good reason to do that. Maybe you want greater, for example, efficiency in the solve. And so you want things to be body fit where it's simple to build the mesh. And then you relax the meshing requirements where it's more complex. Like in this case, you can see that these fillets are actually immersed. So there's no defeaturing that occurs, but the meshing itself is still simple because you can immerse these features And then you can do something, where you kind of take the bulk shape and capture it in the mesh where the rest of the finer features are immersed in the grid. So we call this flex meshing, and it's available in Coreform Flex now. And this is kind of one of the key, I would say, value propositions of what we're building, along with kind of the isogeometric analysis technology. And like I say, traditional FEA uses primarily these linear hat functions, and we use higher order spline functions. So this is what these little quadratic B-spline functions look like. So you can see that they have a little bit wider support, and they're continuous. The first derivative of these functions is continuous across these element boundaries. So today, we can do essentially any kind of BREP CAD automatically, regardless of complexity, and we support most of the major file formats. We're also extending this paradigm to other types of what I would call CAD representations, like, for example, STL data coming out of scanning technology or other other kind of data formats. So instead of reading in a solid model, like a CAD model that you would produce in a standard mechanical CAD package or solid modeling package, you can read it in an STL as the CAD and then perform the same trimming operation and run the same simulation with the same level of quality as you would get with the BREP representation. Okay, so just a very simple example of what we achieve by doing this. So in this case, we take this very simple model here and we immerse it and run a simulation on it. And then this is kind of the thing we see across the board. So this is a simple example, but we see this across kind of all levels of complexity in the simulation, whether it's linear or nonlinear. You can see that for the max principal stress to converge requires orders of magnitude more linear elements than these higher order spline elements, even though they're trimmed. And so you end up with not only this automation, but also superior numerical methods. So, a lot of, I would say, competing technologies sacrifice one or the other. So they give you automation, but then the accuracy or stability or however you want to describe it, you can trust the result less. And so it kind of relegates the tool to a certain kind of application. For us, we're looking for essentially the ability to replace finite elements across all application domains. So here's a little example. Greg will go into this, but I just want to, he's going to show you this in the product. I just want to introduce a little bit of what you're going to see. So here's like a direct ink write pad. The CAD model is on the left, and then the meshing is composed of a body fit mesh for these platens at the top and the bottom, and then we do an immersed mesh for the pad itself. And then the trimming procedure produces the simulation model on the right. And then we can run a simulation directly on that object. So we have contact, highly nonlinear deformations, and nearly incompressible materials. And so this is an advanced application of the technology. And as you can see, it's already in the dynamic nonlinear regime with contact, which is where the vast majority of our customers have applications in those domains, although people are starting to understand that you can now use this as a early stage design tool as well. And so we're seeing more adoption in that area now too. So Coreform Flex is the name of the tool that has both the preprocessor as well as the solver and post-processing capabilities for what we saw on the slides today. And you can see capabilities, and Greg will speak more to that now as we go into the demo portion.
Yeah, so the first demo I want to show is the capabilities that are released today in Coreform Flex. We're going to demonstrate this linear static stress analysis problem that you see on the top right. It's the trunnion supported pipe. for those of you that have a NAFEMS subscription. So it's highlighted in their benchmark magazine. So the feature capabilities that we're just going to show in this are the linear elasticity, as well as defining boundary and load conditions, and then kind of show how we can select those higher order basis functions for our mesh. And then this problem also uses our linear static solver, it utilizes a direct solution method, but it runs in parallel. And then just to kind of, again, emphasize or highlight fully automatic meshing and accurate results. So what I'll do now is I'll switch over to Coreform Flex. You might notice that I'm actually running Coreform Flex in my browser, my Edge browser here. Coreform Flex is also available as a standalone fat client installation, but we built it on web technologies, on browser technologies, to fully support the external cloud, your internal cloud, or kind of air gap node locked compute systems. So with Coreform Flex, we provide some guided tutorials. And so this pressurized pipe example is one of these guided tutorials. Then we can see a journal file here. We have built Coreform Flex to be, again, highly automatable with a command language that is also accessible through Python. Just to show that this is our command console, that every command that we run inside of these other tools that I'm about to show will echo commands. You can see our reset command has already been echoed. And we can even switch over to Python execution if we want. So I'm not going to go into the Python today, but I just want that to be, or for you to be aware of how these tutorials are constructed. So just play a few commands just to load this geometry into our model or into our Coreform Flex, and then kind of give a rundown. So this is a 1/8 symmetry geometry. Even though, isogeometric analysis says that we don't need to do simplification, when there is simple simplification that doesn't take a lot of time, that can be a very powerful tool for users to use. But the key is that in the case that maybe we had buckling and we needed to have a full 3D model, the workflow stays the same. So on the left, we have our model tree. There are really three main items in our model tree. We store the geometry, and this is where we also define our mesh on the geometry, as well as our IGA simulation parameters, and then job management to support things like execution, killing, or managing our jobs that are running. And what I just want to show right now is, as opposed to just going through the journal editor, I just want to show briefly how we might do stuff like assign a boundary condition. So in Coreform Flex, we're going to create a procedure. Procedures are the things that actually do the solves. We'll create a solid mechanics procedure, and I want to now create a boundary condition. So I've added a boundary condition to my procedure, and I want to now create that boundary condition. Maybe I want that to be a displacement boundary condition with 0 displacement on the X, Y, and actually let's do it on the do a Y symmetry here on this face. We'll say that this is on the Y face. We'll call this Y symmetry. And I want to assign that to a set. So as I'm clicking through these different buttons, they're helping me construct both my journal file by, again, echoing those commands, but also then creating these objects for me to now say in my set manager, I have a set where I can call this the Y faces. And now can select those surfaces to make that assignment. But notice that I've assigned this boundary condition directly on my CAD geometry without even having to think about meshability. So, this fillet on this backside, if I wanted to build a body fit mesh in the traditional manner, I'd have to do quite a bit of decomposition of my geometry or just removing that fillet altogether. But I can really leave meshing as an afterthought in my workflow. And I think that's a really important key distinction to make. So that is now fully defined that boundary condition. And now let's just demonstrate applying a mesh to this model. So here I'm just going to my mesh manager where I want to create this parametric space of, say, a quadratic C1 B spline that Mike Scott talked about earlier. And then I want an element size of, I think I want this element size to be size of 5 in each direction. And I'm going to assign that B spline to my part. We can now see the kind of visualization of what that mesh will look like on my geometry. So this is a fairly fine mesh actually for this model. Um, we didn't talk about it today, but we've been doing a lot of experimentation where we've seen that the traditional rules of thumb of having, say, 4 elements or a thickness are really quite overkill for a lot of these problems. But you can see that this mesh does not align with our geometry, and it doesn't have an effect on our accuracy. That's all that meshing is, has been relegated to now, has been currently to choose an element size. And as we get more mature, even choosing your element sizes will be an afterthought. The last thing I wanted to show with this was just, again, choosing our linear time stepping method, or a linear solver, just to create a linear time stepper that then uses our linear solver, and then we can just choose to use our direct, either an LU decomposition or a multifrontal solver. And we'll add additional types of solvers like iterative solvers as we mature. From here, the next step, is to complete filling out all the different boundary conditions and everything, but then really to just create a job, choose how many cores I want to run on, and then launch this job. Then let's just take a look at these results. So this is looking at the von Mises stress with the same kind of bounds that the NAPEMS report shows as well. And we have in our verification manual this example, and we converge to the same solution that multiple different FEA codes that NAPEMS experimented with. We converge that same solution in that same location. We currently, you can see we're showing our results in peer review. We currently export to a VTK format that's native to peer review. We don't currently do any special post-processing of stresses. Many tools will do some volume-weighted averaging to remove kind of what look like kind of these mounds between element boundaries. We currently don't do any of that kind of post-processing, which is why it looks maybe a little bit odd out in the far field. But again, what matters is that we've weakly converged to our solution. The next example I want to show is now where we're going to in the very short term, which is to have we have all of this functionality available in beta, and our partners are currently using these capabilities today. So here we're going to show this nonlinear structural analysis problem that features finite or large deformation, nonlinear contact, a nearly incompressible elasticity. There's a gasket. This blue part here is a gasket. It's nearly incompressible, as well as having metal plasticity active in our problem. And then this uses a nonlinear static solver based on the Newton-Raphson approach, which supports adaptive step sizes and, again, parallel execution. And again, I haven't had to do any defeaturing for this model, other than we just removed the threads from these bolts. So a fully automatic operation in our Qubit pre-processing software as well. So that is also an example. So I'm going to refresh a session here and load up that example. And now in this case, just for speed, I am going to play through the meshing process. So essentially everything right up until running the simulation. And while that's going, I'm going to make sure I've got the other results ready to go. Okay, so while that's running, I'm going to show results first. So in this case, we ran again nonlinear statics, but a scale. We ran our static solver as opposed to a pseudo time of 1 out to a pseudo time of 100 in 22 steps. And just to show an overview, we can see that we're essentially moving these to approximate this bolt load. We're just moving these nuts up the bolt shaft to correspond to our input torque. And we can see then this gasket for this repair, if there is a crack on the top of this pipe, then making contact and deforming with a friction contact so it stays stuck. I think I played. Here we go. Just slow on my computer right now. So then just to look at, right, we can see that so there was a large deformation of things moving and then making into contact. You can even plot by, instead of displacements, let's plot by our von Mises stress and kind of see where we're having the largest stresses in this model kind of occurring around where the edges of the gasket are making contact. And so we're having some bending stresses probably occurring there. So now the meshing is taking place in Coreform Flex. And you can see each of these individual parts is again, in this case, just showing a fully immersed approach. As we mentioned earlier, for simple shapes like the pipe, we could have just done a full body fit mesh. Again, the idea or the goal behind flex meshing is that when you don't have to do, or when it's trivial to build meshes, when automatic meshing tools or semi-automatic meshing tools can find body fit meshes, that's generally preferable. This was a demonstration of doing this entire problem fully immersed. And so I just want to show just a few of these meshes individually. So again, this mesh for this pipe, again, fully immersed. And as you can see, less than a single element through the thickness of that pipe. But because we're a high order, so in our mesh manager, again, we can choose higher orders. We can go quadratic or cubic or quartic or higher even, is why we're allowed to have fewer than one element through the thickness. We look at these clamps, just isolate one of these clamps. And these clamps have these complex fillets on them that, again, take time from an engineer to try to remove those fillets if you want to build a body fit mesh, or having to try to mid-surface to make a shell element representation. Again, that doesn't matter from our approach. We just immerse those in a mesh. And again, as you can see, we actually have fewer than one element through the thickness. In some cases, even half an element through the thickness. And then, yeah, from the solver standpoint, what we have chosen, again, are just pull up the solver real quick. In this case, actually an implicit dynamic solve based on Newton-Raphson, but we can also use our static solver as well. I guess we have multiple solver settings in here for implicit dynamic, various implicit dynamic with quasi-static and fully implicit. The last example I want to show is this ball drop test, which demonstrates nonlinear dynamics. Again, with large deformation, nonlinear contact, a nearly incompressible solid, isotropic plasticity available, but then with explicit time integration in this case. So again, this is another example in our Coreform Flex, this ball drop test. And as you can see, again, a fairly complex geometry. If I were going to do this model with traditional approaches, I would remove all of these little fillets, and then I could probably mesh it from the inside outwards with a sweep. But then I've lost those fillets, and so I've kind of changed the problem. But again, with a flex meshing approach, you can just say that maybe in this case, I want a cubic C2 um, uh, mesh for this with maybe an element size of 3 in each direction, and then assign that to the ball. And that part's now meshed. That's how easy meshing has been has become now with this method. Um, and then from our time stepping method here, just we have a central difference explicit dynamic time stepper that executes. And this problem runs in about, I think, 5 minutes total. But that is now how easy this problem is to run. We also use general or a base contact formulation, where from a user standpoint, all that has to be done is to define a single interaction of mechanical contact with a base contact. And so I haven't even had to specify, um, you know, different sets to be in contact. Haven't had to do a whole bunch of button clicking. Um, it's just automatically specified now. The default will be a frictionless contact, and I could assign friction if I wanted to. So let's take a look at these results now. I'll just play this animation. And here you just see like this ball again makes contact and then bounces off of this ball and over a 5 millisecond time interval. And then again, plotting here the max principal stresses, you can kind of see the max tensile stresses are kind of occurring on these fillets on the interior of the ball. And that's where if I had removed those fillets, right, then I'm gonna have to do uh, you know, more hand calculations on my end to approximate what would the maximum stresses there have been, and rules of thumb for that. Maybe even make a breakout model just to simplify the problem. But without having to defeature, I don't have to worry about those modeling assumptions that have come into play. So those are the demos I wanted to share with you. Again, those are available today in Coreform Flex. We provide them with our standard installation. You can explore quickly the different capabilities in Coreform Flex.
Thank you, Greg.
Yep.
Let's, okay, so just briefly before we move to questions and answers, if you'd like to try Coreform Flex, we kind of have a procedure that we've found to be successful. And I wanted to just introduce you to that because I imagine there'll be questions about how to try it. So first step is contact Matt at that email address. And then usually what we do is we don't want to waste your time. So we usually will have a discussion with you about what you want to do so that we can clearly, tell you if we can solve your problem or not. And then if we feel like we can, we usually identify with you a problem of interest, which we then, our internal engineering team will solve for you and provide some feedback so that you can kind of see how it was done. And then we'll share those results, the setup file with you and all of the other data that you might want. And then we give you access to try Coreform Flex yourself. So that's our kind of our standard process. And of course, it can be tailored to each customer if there are unique needs. Okay, so let's move to Q&A. So anybody that would like to ask a question, I'm not sure.
Mike, there's a question from Yuri. What could be the accuracy of the solution in the element where we have 90% void space? If I have a plate with a thickness of 1 millimeter and use a background mesh of 10 millimeters, for example.
Yeah, that's a very common thing that we do. For example, with higher order splines, if you're doing thin structural members with this approach, then the higher order smooth splines actually get you very good bending behavior with these kind of partial elements through the thickness. And so, if the rule of, in traditional linear FEA, usually there's kind of a rule of thumb that you have a certain number of elements through the thickness of a shell object, for example. Here, we don't have that. We tend to, if you move up in degree and smoothness, you can actually essentially achieve almost arbitrarily accurate simulation results. So, because, bending is by its very nature kind of a higher order effect. And so higher order functions allow you to capture that even if you don't have a full element through the thickness.
And then there's another question that maybe I'll take a stab at answering from Bruce. If I have a Creo CAD assembly model with hundreds of parts and dozens of subassemblies, can I try Coreform Flex for this model? The way I'd answer that today is that is our goal and our vision is we're building this tool to be able to solve with assemblies. The best way to find out is to talk to us and have us take a look at it. But we support contact and constraints between different parts of assemblies. Coreform Flex is still a young solver, and so probably the most prohibitive part is just working towards performance for that assembly. But the best way to know is just to reach out to Matt and have us take a look at your problem. But that is the vision of Coreform Flex.
Yeah, and I would say about 90% of our customers that we're working with currently, I mean, can't think of any problem that's not an assembly, honestly. So everything that we're doing is mostly in that regime.
There's another question about the materials available in Coreform Flex, whether there's nonlinear material properties available or composite material models available. Mike, if you want to answer that question.
Yes. So currently, we're going to release in a couple of weeks some very simple neo-Hookean nonlinear materials. In the Q4 release, we'll have plastic materials and a few viscoelastic models as well. Our approach to material modeling has been to introduce some of the basic material models that you would want, and then we're adding the specific material models that our customers are asking for.
And then maybe along that line too, Brady asks, how difficult is it to implement custom constitutive models, and what does that process look like?
Yeah, Gray, you could probably answer that. What is the
Yeah, so we use Julia for our user subroutine language. We haven't yet hooked up available to end users the ability to use Julia to define custom constitutive models, but we have done that in the past and is one of our kind of early stage development activities. So for those who might be familiar with traditional tools, where you oftentimes have to write either Fortran or C code and then find a compiler for each system that you're going to run on. Since Julia is just in time compiled and performant, it's actually quite easy to define those constitutive models in practice. Another question from Bruce is about whether or not we have quantitative error estimation and mesh adaptation in Coreform.
We do not have that today, but we do have a lot of experience in that area, and splines lend themselves to very powerful local mesh adaptation procedures. That's a capability that will show up in 2025, probably towards the second half of 2025.
And then
let me say one thing. Let me say
Yes.
one thing more about that, though. I shouldn't say we don't have any mesh adaptation, because you can vary the mesh size part by part. So there is kind of a part local adaptation that can be performed. So if you have 15 parts, let's say you had some that were like threaded screws, for example, you could have a very fine mesh there and then a very coarse mesh in other places, other parts. But in terms of being element local, like zooming into a region, with like a few elements and refining just those elements, that's not something that we have today.
And then maybe somewhat related to the previous question on the user materials, someone's interested in welding simulation and wants to be able to pass torch trajectories for the welder. And again, that Julia user subroutine is currently available to define general functions for stuff like boundary conditions, or like where to like put a heat flux. So that today is possible to do in Coreform Flex today. Define a Julia subroutine to define a path. And of course, that path could be in a CSV file, a text file, or an Excel file, and use Julia to just read in those points, interpolate between them. So it's a fully functional capability there. And Sumit asks a question, Mike, that I think you kind of touched on, but the question is, how fast or slow is the rate of mesh convergence for this method compared to traditional FEA?
Okay, so it is a finite element method, and the rate of convergence basically is dictated. Let's say we're dealing with, sufficiently smooth problems. The rate of convergence is order p plus 1, where p is the degree of the polynomial that's being used in the function space. So if you have a linear finite element method, the order of convergence is 2. And with our methods, since they're higher order, the rate of convergence is much faster. So if you're using, for example, a cubic B-spline, then the rate of convergence, like in the L2 norm, would be 4. So that would be like convergence rate of displacements would be order 4. Convergence rate of the stresses, since they're a derivative of the displacements, is 1 order less. So it would be order 3. So as you go up in degree, the rate of convergence increases as well.
All right. Another question from Yuri is, could your solver continue working with heavy mesh distortion such as non-uniform foam compression?
Yes, this is an area where our customers specifically use our tool to accomplish just this. And the smooth spline function, the deformation patterns, because of the smoothness, are also smooth and distributed more evenly across the mesh. And what this means is that in general, you can distort our meshes, I would say maybe a factor of 2 or 3 more than linear finite elements for a given application. There is a limit of mesh distortion, even in our capability, where you might invert an element and then, the solver will break down. But in general, that point arrives much later in the deformation.
Thank you. There's also a question about whether or not we can handle contact between two flexible bodies. And I think the answer to that is absolutely yes. What you've seen today with the ball drop, the pipe repair clamp, as well as the those direct ink write pads, we also have additional internal verification and regression tests of not just two flexible bodies, but multiple flexible bodies in contact. Again, being able to use even just that base contact formulation to simplify the setup. And then there's another question about the current status for defining multi-material type parts or geometries, such as multiple material models or properties across a single part. And the current status is that we don't yet have support for that, but that is on our roadmap to support, both in like the traditional approach where you say segment off a region of your part to have a specific property, or to define some sort of field that defines say like a graded material Those are on our roadmap, but are not available today currently. If you wanted to do that today currently, you'd essentially take your one part and turn it into two parts within a bonded interface between them, between those two regions. So it's not as straightforward as we eventually want it to be, but that is where we want to go with the tool. And then there's a few other questions that maybe would be perhaps best answered via email or on through our forum. But I guess one additional question I think is good for us to answer is from Omid about what export formats does Flex support? He's asking for import back into Qubit or other FEA tools.
Okay.
And so, yeah.
Go ahead, Greg. You can
Yeah.
take.
So I guess the thing I'll say is that if you've been following Coreform for a while, I'll maybe even share my screen briefly here. Is Coreform does support the Coreform, develops and distributes Coreform Qubit, which is a traditional meshing tool. And so, for instance, with this direct ink write pad, what we support today is being able to say build these body fit meshes in Qubit, where I want to maybe still immerse this the pad, and we can actually export this to the native Flex format, which is called Coreform CF file. And then that CF file is then what's native to Coreform Flex. So we can then open a CF file in Coreform Flex. We could also save our current session as a CF file. We don't yet support the backward capability where if you've saved a CF file in Flex, it currently cannot be opened in Coreform Qubit, just due to different versions of the underlying CAD geometry kernel, those will be synchronized in a future release of Coreform Flex in Coreform Qubit, at which point we'll then support the backwards import functionality. As far as other tools, we don't support any other pre-processing tools being able to import the CF file. If you have specific needs, you can reach out to us or reach out to Matt with your specific needs.
One, it says, what is the long-term strategy for Coreform to compete with gold standard solvers such as Abacus, Dyna, Nastran, and Ansys, or compete with pre-processors, provide hex meshing and IGA capabilities? So for Coreform Flex, we're competing with standard solvers like Abacus. We do have a preprocessor for our solver, and that preprocessor can produce spline representations that can be consumed by solvers that accommodate what's called Bezier extraction. This is only available, to my knowledge, in Dyna commercially. And so Qubit, our other product, Coreform Qubit, competes directly with Hypermesh and ANSA. And so I think our tool, we have two different tools. Coreform Flex is primarily focused on competing in the solver space, and Coreform Qubit competes in the pre-processing space.